This absolutely crushes it, Gate, as far as what I've been looking for. I saw this and I was like, yeah, baby. NP right here, nitrogen and phosphorus, as far as what I'm doing. I mean, of course, he didn't know to the prior set to this and the time frequency. He was going to have a Nutella commercial. You know how good you would need to be with the time tech curve over 3 years to be able to predict that, adding it to the garden and students and shit like that. Of course, we're going to use a food brand thing instead of a computer number about what this is. Fast Fourier transformation and time frequency and time and function frequency domains. I just want to give him Steve here from 3 years ago his credit.
Welcome back. So this is our warm-up lecture of how to use the fast Fourier transform in Python. And so in this lecture, what I'm going to do is create a really simple data set, which is just the sum of two sine waves of different frequencies.
Hi.
We're going to add noise to that data set, and we're going to use the fast Fourier transform to pull out kind of the structure in the data and denoise. Okay? So in this example, we're going to see what the fast Fourier transform is, how you apply it to data, and how you actually do that in Python. Okay, so this is the code. The first thing we're going to do is we're going to create our signal with two frequencies. So we're going to have a time step of 0.001 samples per second, and we're going to have a data set that goes from time 0 to time 1, which is the sum of this sine wave with frequency 50 hertz and this sine wave with frequency 120 hertz. Okay, so we're going to add up those two pure tone sine waves.
Having to need a triple body problem like a plant.
We're going to take that clean signal F, and we're going to add a bunch of random white noise to it. Okay, and in fact, this is actually quite a lot of random noise. So if I add up two sine waves, then kind of the maximum variation I can get is plus or minus 2. I'm adding white noise with magnitude 2.5. So this is a lot of random noise. And now I'm just going to plot both the clean signal and the noisy signal here. So you can see
chromatics on the screen, both of them in the screen, makes neutrons
this is a data set in time, and this is the signal. In white here, we have the clean two-tone sine wave, which is 50 hertz plus 120 hertz, and red is the noisy data once you add that Gaussian white noise on top. Okay? And so we're going to play a game. We're going to act like someone sent us this red data and didn't tell us anything about the low-dimensional structure, that this was just two sine waves added up. So we're only going to get the red data, and we're going to have to infer kind of what the clean denoise signal would be using this fast Fourier transform. Okay? So the first thing we do is we actually compute the fast Fourier transform.
Before the black hole and after the black hole.
And in pretty much every programming language, this is super simple because it's so fundamental and you want to use it all the time. They've made it as simple as possible. So in NumPy, you just run this FFT command. So numpy.fft.fft, and you give it the data F and the length of that data n, how many data points there are, and it returns f hat.
Technically, I can't argue with
so just to remember, we have our data f,
0 to 1, but the question
which is an
am I
effector.
starting with 118?
We're going to run it through this FFT command,
that NPK and, that
and we're going to get this vector f hat.
You need
Fourier
that
coefficients.
HTLM,
okay, these are complex valued Fourier coefficients that tell you how much kind of magnitude, what are the magnitude and phase of the sine and cosine components of increasing frequency you would have to add up to get this data set. Okay, so these are complex values with a magnitude and a phase.
Back to your garden.
The magnitude tells you how important that particular frequency is. The phase tells you if it's more cosine or sine and what mixture. Okay? And once you have this Fourier transform, now what we're going to do is compute the power spectral density, the PSD, which is just f hat times the conjugate of f hat divided by n.
Y
and so I like to think of this
these frequencies.
If you take lambda, some complex number lambda times lambda conjugate, this is essentially going to give you the magnitude of lambda squared. If this is a complex number, I'm just going to write this out for you. Lambda equals a plus ib. So lambda conjugate would be a
to frequency
minus ib.
To wave function. Okay,
and so if you multiply lambda times lambda bar, you get a squared minus I squared times b squared,
ragdoll physics pretty
a squared plus b squared. Okay, so lambda times lambda bar, or lambda conjugate, just gives you the magnitude of lambda squared.
3 years.
And that's what we're doing here with
service
f
maintenance.
So we're computing the magnitude of each Fourier coefficient squared, and we're going to get a vector of powers at each frequency. Okay, and you can convince yourself that if this is a function of time, then these each frequency has units of per second. These will be in units of hertz.
When that frequency
and so you can convince yourself that if I take f hat times its conjugate, this will have kind of units of power.
2 foot by 2 foot.
So this is the power spectral density that we're computing here.
Inches deep.
Then I have to compute this vector of frequencies. So each entry in here corresponds to a particular frequency from low frequency to high frequency. And so I have to actually build a vector of all of those frequencies in this freak vector. And now what I'm going to do is